when we first wrote this and tried to publish it, people basically said to us, you guys are nut jobs. You don't know what you're talking about. You're young and you don't know the field, and you're just very naive. And it's kind of sad. Hashtag sad. It's a system that's just absolutely shocking. And I think in 20 years or maybe 50, people are going to say, wow, you guys lost generations of wonderful, creative, exciting scholars by putting them into this ridiculous system of what counts as success and what counts as, what the meritocracy is about and how you publish and how you assign beans.
This is Brain Inspired.
Hey everyone, this is Paul Middlebrooks, here again with David Poeppel for the second part of our conversation about speech processing, language, understanding, the neural basis of all of that, and some of the recent progress in AI on that front, plus plenty more, including David's thoughts on how we are failing to provide graduate students with the right environment to become great scientists. If you missed the first part, you should listen to it first, episode 46, because this picks up where that left off. We were basically in mid-conversation. Thank you for listening, and if you like the show, consider a tiny $2 or $4 per month contribution through Patreon. You can go to braininspired.co to find the red Patreon button there to click. I am a solo act, no big podcast production company, no massive university or company backing me. It's just me, my guests, and you guys. So thank you in advance, and thanks to all my supporters on Patreon out there. It's astounding and super encouraging. You could also reach out to me with questions and or suggestions on Twitter. I'm at PGMid, PGMID, or email paul@braininspired.co. Okay, here is the loving curmudgeon who wants us all to do the best science that we can, David Poeppel. Since we're talking about oscillations in time, it might be a good time to transition and talk a little bit about AI and deep learning. Mm-hmm. Because, dynamics are important in our cognition, as we were just talking about, but it's not, dynamics aren't so much important in deep learning nets, right? So there's been a ton of progress in natural language processing, doing things like translating between languages, speech recognition, summarizing texts, and so on. Are you familiar with the transformer model for NLP that Google created at all?
Yeah, it's all the rage, and certainly in Europe.
I bet.
I was just at a meeting in Holland where people were just going nuts about
how great it is.
Their transformers.
Oh yeah. Well, So there's that track. There's also I'm sure you're familiar with this recent work out of Josh McDermott's lab, creating these deep networks to, so I had Dan Yeamans on the show, mm-hmm. and some other people who have talked about, have worked on these deep learning networks that have replicated some of the findings in the visual stream, right? In the visual stream, object recognition stream in particular.
Yeah, there's a certain kind of fervor of argumentation in that line of work coming from Jim DiCarlo's lab.
Yeah, fervor is a good word, yeah.
And Dan Yeamans did the work there, and of course Josh was formerly here and worked on stuff together too.
That's right.
Really gone on board with that and sort of translated some of that to the auditory case, which is interesting and looks like a potentially promising way.
Yeah, So I mean, there's this. I think it's Nature Neuroscience. The network that I'm talking about, where they, similar to the visual stream, they sort of replicated behavioral findings and some auditory tasks.
Yes. And
you see the same kinds of representations at some levels in the network as you see in neurons, for example, in brains. And actually, they found that the best network that they trained, so they did a speech task and a music task, mm-hmm. and the best quote unquote network was actually two separate networks.
with different ones, yeah.
Yeah,
it's consistent with Josh, and with other work from that lab and other labs, and that actually Sam Norman Hagner, former student there, and has done on really the in some sense refinding a more modular organization of speech and music. So that's interesting. And so and the network results are quite, recapitulate that, what the imaging results had shown. And actually what lesion results show too, is that there's a considerable segregation of function when you compare speech and music. It's not that surprising. They're not the same animal,
right?
But it's cool to show it, and I think it's quite interesting that the architectures these guys were pursuing, which in this very cool work, are it's not the same animal.
Yeah.
One concern about that is different things are different, and so that's
you heard it here, folks. Well, so one of the things that like deep learning nets sort of implicitly assume is that the neuron is the right level of analysis, right?
The right hypnotization of the problem.
Yeah, they don't train on oscillations, for instance,
yes,
right?
That's right.
So I'm just kind of curious in general on your take, like, how has deep learning, do you think, contributed to or affected our understanding of auditory and speech processing?
I mean, so it's just beginning to, right? In the sense that, let's take actually I think it was Josh who there was an interesting workshop probably organized by Josh at MIT about 2 years ago or so, where a bunch of us and a bunch of the deep learning people were sitting together for a couple of days trying to get our head around sort of what are the different performance of things. And of course, the performance of the ASR systems is kind of awesome now, right? Assuming there's no noise, it's the same speaker, you don't have an accent, you don't have a cold, you have
to enter your accent, yeah.
So the performance is, amazing, although not as amazing as any 2-year-old. So but one of the interesting things was one of the things that could be, for instance, an interface. It may or may not be necessary, right? Remember that for those guys, of course. For the people working on the engineering problem, performance is the ultimate. Performance on kind of benchmark tests is what they're about, and it's not of interest what a cognitive system does. That's not their business. But it's interesting, nevertheless, to sort of exchange ideas. And one of the things that we do particularly well is what we were talking about a bit earlier, which is the segmentation issue. Like, we're really good, in a language that we speak, to just chunk stuff up. And we use physical cues, like, for instance, the amplitude envelope, because it's an obvious one. And then we use other cues, for instance, that we have knowledge of vocabulary, we have all kinds of top-down information. So we're really good at unitizing the problem as the signal comes in, which makes the decoding problem easier. And so one of the discussions we had, which I thought was quite interesting, is what would happen if you enrich a really, an ASR system built on a deep learning architecture with rhythmic activity of some form that capitalizes on that. Okay. And there were some interesting, and I don't think the results are in it, but there were some discussions about how to do that, when to do that, and would that actually tweak your performance in a bit, because that's something that you get sort of for free from the human auditory system, from even the afferent system.
Well, it's free, but it's also a constraint, right? I mean,
it's a great constraint, and it could actually boost performance. And so it would, let's say, reduce the search space for a deep learning system, because you say, look, here's a chunk, go find me that. And so there's interesting potential interaction between that. To what extent these architectures, what's your favorite transformer, DNN, CNN, LSTM, for your system is, I mean, it's not yet clear from the cogneuro point of view. And I think it's a little early days. I mean, I think Josh is one of the first people to really work on it very effectively in an interesting way. It's beginning to sort of penetrate the field, but it's not so obvious what the questions are other than being descriptive, right? Yeah. It's just to say, well, I have a network that recapitulates what we knew about the network is good. It's a really good first result. It's a little bit like the early work on the ventral visual stream, that, your 144 layer CNN can be probed, and you find something that's a little bit like, before, that's cool. The question is, where does that go? Is that just a redescription of the system? Or, is it really capturing something deep? Is it making interesting predictions in some way? Does it do, I think that some of the work extending what is a reasonable, how can you drive cells into some weird perceptual space by saying, I've recreated the optimal stimulus by, well, by reverse engineering, what is the best thing for my receptive field? Can I make a super stimulus, right? Can I make a stimulus that drives a cell even more than a naturalistic stimulus, right? That was a recent paper by the DiCarlo lab, which I thought was pretty cool and weird. And
the images were weird, yeah.
Images are like, some kind of tripping thing, right?
Yeah. That makes sense, yeah.
So one could imagine doing something like that for the auditory case. So let's say we look at that and we say, hey, it turns out that, tonotopy, which is, by the way, one of my least favorite concepts, boring as all hell, probably not useful. You heard also that here first.
Okay.
Will not make me any friends, but tonotopy is not as useful as retinotopy.
How do you keep friends, sir?
I don't have friends. I'm just trying to be nice to my family. So
That's hard enough.
It's hard. That's already a lot of work. No, so it's conceivable that we end up with interesting stimulus parameters that are more powerful drivers of, let's say, cortical cells than we have. I mean, right now, like, how many times you can listen to a talk with, we played, 400 hertz, 1,000 hertz, and 3,000 hertz, and they were different. Okay. Right. Differences are different. That's right. And the question is, does it do anything for you? Is it relevant? Is that spatial arrangement even relevant at the sound pressure levels that we use when we speak or hear? I mean, there's a lot of open questions about this stuff. It's a very coarse thing. So we could use this to inform a little bit about what kinds of things the auditory cortex is sensitive to, which would be really useful, because our understanding, unlike the visual case, our understanding of the human auditory cortex is not awesome. It's not. So we've imported, so there's partly because it's just painstaking work that hasn't been done, or is done by very few labs. It's yeoman's work, unbelievably important, just to do the anatomy and the histology and the staining on human cortical tissue. That's just, there's very, very few data sets because it's a pain in the neck, right? And so there's a big lab in Germany that does a lot of anatomy, led by Katrin Amunds, does very important work on this. But it's a little bit shameful how little we know about, here we are very casually talking about, like the old Fellman and Van Essen diagram, and everything connects to everything. But if you ask for something like that for human auditory cortex, well, we look to the macaque. Well, there's some beautiful stuff by Preuss and John Koss and colleagues that have done some stuff, but that's not the human auditory cortex, and they're quite different, actually. Right. Like, we speak and do other interesting stuff that, and so there the animal model stuff becomes really tenuous. I mean, we really need a parochial model, in the sense that, parochial to us, like to the human brain. And that's a really important intermediate step. And whoever does that and really is going to do a huge, huge service. I mean, there's endless studies going on still defining, primary auditory cortex, core auditory cortex. And I'm like, that's
never ending. Yeah.
But let's just, someone has to do the hard, difficult work of doing what was done, for 100 years in the animal preps, which is doing, the careful histology, the staining, the lining up, the segregation. Are there boundaries? Are there not? I know it's difficult. I think the techniques are getting better. The automatized analysis is getting better, but we simply are still struggling with these basic questions about structure.
I mean, this really contrasts with the hype that deep learning has brought recently. And are you optimistic? Are you pessimistic
I'm very optimistic about it as an engineering thing, and I'm very pessimistic about artificial general intelligence.
Well, about its use in helping us understand cognition.
Yeah, there I'm, I guess, because I'm a grumpy middle-aged guy, there's a sort of age thing. You're my age, you don't know anything. If you're between my age and 30, you really have lived a life of MATLAB. And if you're under 30, you're just a creature of Python.
Right.
That's how life is structured from my perspective. I guess I'm seduced by the excitement of the results. Yeah. I think it's really interesting. And the fact that engineering solutions that are sort of brute force mechanisms, this is what I was saying earlier, is science become regression? So brute force big data mechanisms are it's impressive to me that they work across a range of tasks. It's not obvious to me that that's the way we want to go in terms of understanding cognition, perception, human brain organization. In the sense that obviously we don't work on billions of training examples and learn discriminate. We have a slightly different architecture, but more importantly, that can probably be solved, and you can do kind of wickedly cool, not unsupervised learning things. But and even on sparse examples and stuff like that, right? So but what I'm more interested in is that the kinds of problems that we solve are the problems of common sense, and they seem much less tractable than the problems of data. So the problems of common sense are the kind of stuff that people in robotics face, right? So I can walk upstairs and get my keys, and I can walk back. Yeah. Like that's not a trivial problem, right? As it turns out, but it is actually a trivial problem. Or you can tell me, can you just quickly go back to your place and pick up, that book? Like I can do that, and I'm sort of moved by the fact that those systems are extremely good, and I think always have been. I mean, they're just better now, right? But they're good at the kind of stuff that requires pattern matching and handling large amounts of data. But they're less good at things that we actually do, which is having a conversation, navigating my way home, watching. Although you can do Roomba, but that's hardly navigation.
I wish I had one.
It's cool.
Yeah.
The kind of and common sense conception, right? So things that aren't so chess or Go is one thing, but sort of conversationally appropriate chit chat over lunch is another.
But see, there are a lot of people working on this, and they actually do use Bayesian concepts a lot.
Bayesian prediction. Yeah.
Bayesian prediction. That's right.
But are you optimistic about that? I mean, so what do you want to, the question is what do you want to understand? Do you want to understand the system that generates it, or do you want to understand how we work? And I guess I'm on the latter camp. I'm in this, I'm impressed by the engineering solution, but I'm in a department of neuroscience and psychology because I'm interested in how our stuff is organized.
Yeah. I mean, Richard Feynman famously had on his chalkboard when he died, it's something to the effect of, I do not understand what I cannot build.
Cannot build, yeah.
But building something doesn't mean that you do understand it.
No, not at all. I mean, I think Feynman is wrong, as rarely, but occasionally.
Yeah. So here we have deep nets where you are building, let's say, cognitive function in some sense.
But look, I mean, forget the cognitive function. So here's a concrete case where I think the deep net stuff could be really useful. Is we could learn from the stuff that the vision community has implemented pretty successfully. And maybe we could use that to solve one of the problems that, like I said earlier, why is it that we have such poor understanding of anatomy?
As a tool. Yeah. Use it as a tool.
So use it as a tool to learn some basic properties of the structure of that thing that's just been resistant, right? So make some predictions. So for that kind of exercise, feeding in a lot of data and doing some classification and clustering is super useful. You can say, actually, I predict that, you need to look for, 9 things. I mean, whatever turns out, it would give us a sort of heuristic device to take a bunch of data and kind of somehow structure the search problem for us to say, actually, this would be a reasonable subdivision.
Yeah.
And it might not have anything to do with, let's say, the macaque subdivision, the bird subdivision, whatever is going to be next, whatever non-human primate is, next on our list subdivision. We just don't know. And we have to be, this is why we want to be parochial. The human auditory system might have properties that are a little bit different because of the incredibly rich interaction with the motor system and the thinking system, right? So the kind of multi-stream model that I've worked on for many years as a kind of fundamental principle of the speech and language systems,
which we're not even going to have time to talk about the dual stream.
That's
it's like your major contribution that people always go back to. Yeah.
Cited early, cited often.
There you go.
It's now, that's sort of like I'll tell you a brief story about that just for fun. But the issue is that, so I could imagine a very beautiful contribution to that because, we all build on, we read the anatomy and physiology from the monkey literature and say, okay, so let's assume that that's a good model. There's maybe tonotopic areas and this is their arrangement and there's core areas and belt areas surrounding the core areas and so on. But look, the human's auditory system and its environs have to do slightly different things. Namely, they have to create the infrastructure to link seamlessly to the motor system, to the speech motor system, and seamlessly to the recognition and memory systems that are very different in kind. Mm-hmm. And so these are extremely different kinds of demands. And so it stands to reason that the intermediate layers of analysis are quite different. So take A1, right? So there's no reason to believe that primary auditory cortex is structurally or functionally that similar to primary visual cortex. Right. In fact, it's much more likely that the inferior colliculus is similar to V1. Hmm. So that's the kind of representational, fine-grained orthogonalization and granulation of the problem. A1, or, that might be multiple areas because there's multiple targets going to A1, might already be doing something quite different in kind in terms of the, let's say, transformations it does on the input. And so we have to look for different things. And I could imagine a really amazing contribution of the DeepNet kind of approach could be to make data-driven suggestions or kind of heuristically derived hypotheses about what to even look for.
Yeah, I like that.
That would be a really big and cool content. And if any graduate student ever listens to this, go run, do it.
Yeah,
you'll be rich and you'll be famous. Maybe not rich.
Yeah, right.
It'd be a really great scientific contribution for a big chunk of the field. It's like a good project.
Take a break. A few deep breaths. Today's quote of the show. Within a generation, the problem of creating artificial intelligence will substantially be solved. That would be Marvin Minsky, 1967. So you're pessimistic about artificial general intelligence, you were starting to say.
I'm pretty pessimistic about that. There I hold it with my, with the fact that we just don't understand how the mind works at all. And so, pattern matching and sort of so simple. Also, Bayesian predicted pseudo common sense, a mind not makes.
Well, we don't even know the right questions to ask. I think it's a problem. Yeah.
Yeah, I think that's just too. I think it's it's obviously, a big goal, and it's kind of a fun goal.
That's fun. It's
sort of fictiony, and I can get into why people want to do that, but I just don't think it's just not right. Just work on something that we can actually get some traction on.
Well, I don't even know what it would look like. How would we know if we built something that was generally intelligent? I don't even know what that means. I don't know what it means.
I don't know what intelligence means. I don't know if it's like I said, I have problems understanding how you recognize a single word. So, since I'm stuck with that.
Right. Yeah.
Which is a seemingly banal problem. I'm really hosed when it comes to artificial general intelligence so there are solutions. So one of the properties of general intelligence, as far as I'm concerned, is the issue of compositionality. And there are some solutions for that. But the problem of compositionality is just one, and it doesn't just mean that you can, let's say, look up, concatenate, and form a new representation that takes on the interpretation of its parts, but in a joint sense. But also, then that becomes an inferential step for the next. Thought is a difficult thing, very, very difficult thing. We started with thought.
Yes,
and I maintain that thought is not a gimme. Thought is a really hard problem. So. Well, I want to tell you that just because, as a sociological point, so should there ever be a younger listener to this, the thing about the dual stream that I think is a sort of funny thing. So this is an idea that my friend and colleague Greg Haycock and I have worked on since actually around my dissertation, since the late 90s. We wrote our first paper on this in 2000, and another one in 2004, and another one a little later, and it's become quite influential.
It's the standard. It's the standard model now, isn't it?
It's not. Yeah. So, but here's the funny thing about this: when we first wrote this stuff, basically, the moral of the story is we never had any good years. When we first wrote this and tried to publish it, people basically said to us, you guys are nut jobs. You don't know what you're talking about. You're young and you don't know the field, and you're just very naive, and it's kind of sad. Hashtag sad. We had some pretty nasty commentary, and we were youngish or whatever, and we were not so amused and didn't have a thick skin.
Right.
We were like, thanks a lot. So, but then eventually people were like, hey, maybe it's not that dumb because look, it was a straight lift from vision, right? We just said, well, if this is a fundamental organization of cortical systems and this is actually a useful computational subdivision, what would it look like for, a language system? So we thought, let's just kind of reason through it from the point of view of, lesion data, imaging data, physiology. What would such a system look like? And we thought, okay, it's not such a terrible idea. Jesus, it's just But so first we got absolutely, reamed, and we still have some of those old reviews.
Oh, good.
Yeah, Greg was reading me some of those. They were not fun. And then, so now we go to conferences, and now we're like the old guys who are like, well, that's obviously the old school stuff. I'm like, thanks. When were the years when you were just hanging? So we had a very quick U-shape. We had hatred, brief acceptance, and hatred. So now basically it's become the sort of, the model that you put up at the beginning of your talk and say, well, here's the old standard model. Now let me take some shots at why it's wrong. I mean, that's good. It's kind of, it's how progress should be. But we were always like, we wanted just 1 year or two of happy times.
Yeah. How does that feel that doesn't normally happen. There is usually, a decade, where people get to win awards and things for their...
Yeah, an award something. You're not just like the old fart. I mean, it's fine. We're happy that it's been a very useful heuristic model, and it's made some, progress, and there's some support for it, and there's, some subparts that work well and others that don't.
Yeah.
So we're still pretty attached. I mean, I think it's probably wrong in an interesting way.
Oh, so yeah.
It's underspecified to be sure. I mean, there's no such thing as, as in the vision case, we now know, there's way more organization to it. But as a first cut of sort of subdividing, again, it was very Marian inspired. Like, how do you subdivide the computational problems if there are different processing streams? And we thought, well, if the visual case is a sort of what, how, or what versus where kind of stream, the way it was originally proposed by Jerry Schneider, I believe, for the hamster.
Oh, wow.
From the colliculus, actually, multiple visual streams, and then later on by Ungerleider and Mishkin for macaque visual cortex. But it was really an older paper by Jerry Schneider that initially did the multiple streams in vision.
Interesting.
And I think it's a 1967 science paper. That was the initial impetus for really thinking about this kind of segregation. And then I think, the more, obviously the Mishkin and Ungerleider thing was unbelievably then influential. Yeah. And we simply took that notion because it seemed to make a very sensible subdivision, not just for vision, but possibly for perception. In the language case, namely the interface to production systems and the interface to meaning or, representational structural systems. And then we just tried to rehearse the argument of what would follow from it, what would be the parts. And of course, that was now 10 years ago or more.
More.
I mean, the kind of standard version. And we're now working on the next version, unsurprisingly. And, but it's actually held up pretty well for now in terms of its empirical basis. And there's not the general idea of this, and that's probably just because cortexes are organized that way. Mm-hmm. So we just happened to import the right metaphor from the vision case because it was, and it's probably just a very useful match between implementation and computation in the sense that somehow evolution has figured out, look, these very broad problems are best solved by specializing your cells to do this or that. Like maybe this bunch of cells is really good at coordinate transformation. And it's just, some kind of basis function of this or that. And that seems like a really old idea in terms of evolutionary mechanisms. And so the fact that it would be recycled is, in retrospect, not that surprising.
Well, I have this, I don't know, I've been, everything seems dual, and there's no reason why it needs to be just dual. At some point, a process has to split in two, but then it can keep splitting. And
that's true. I mean, it could, and it probably does. But I mean, so in the visual case, for a while, there was the truel thing, right? There was a third stream in the visual case, but maybe there is subsplitting. I mean, I think that the two thing is just a really broad subdivision, and I think you're absolutely right. So, for instance, in our case, the dorsal stream stuff, I've worked a bunch on that in the last couple of years, actually, with some of my friends here. And we have a lot of stuff to say about sort of, subroutines that are supported by that.
Yeah.
So you're quite right. It's not that it's a monolithic kind of, chunk of wires. I mean, there's subparts responsible for different things, but arguably, well, they share at the very least the same, or at least partially the same origin, and maybe some overlapping things in terms of the targets. But it may be that, for instance, there, just anatomically, there's no dorsal stream. There's like 3 or 4.
Yeah, right.
And they have different origins, right? It's different whether if you originate in the middle temporal gyrus or more, a little bit more posterior than that. That means your input is quite different, and to whatever whatever gets sort of read out at the other stage. Is it more dorsal premotor cortex? Is it more into conventional Broca's area, whatever that is, and so on and so forth. So there's no sense of there's no monolithic thing at all. It's just totally fractionated.
See, that's the problem. The brain is complex. Let's just quit and study deep learning.
This is part. Maybe that isn't. The complexity is disheartening. Because every time you look closer with a new machine, you find there's like 20 more things to look at. Right?
Don't look closer. Don't look any closer.
Yes, that's exactly. Yeah, every time you look closer, it's like, oh, it was pretty good when we just had dendrites. Now we have spines.
Yeah.
And then the locus of activity becomes the smaller thing always, right? So if you're a vision person, you now work on the spines of the V1 neuron.
That's right. We're going to get down to atoms. You'll see.
We'll be there.
Yeah. So I can hear John Krakauer just seething right now.
Nonsense. You don't need the vaguest idea.
You don't need to know what neurons are doing. Yeah. So that was my poor impersonation. So this has been a long time, and we didn't even get into your music research. I want to talk about what you used to call, I want to pull it up because you call it the maps and mapping problem, which you kind of touched on a little bit. And you used to call it the granularity.
The granularity mismatch
problem and
the ontological
incommensurability problem.
That's some serious shit.
Yeah. That is some serious shit.
I can give you a quick. Things that I care about in terms of this issue with these pretentious words, right? So let me unpack them a little bit. So some years ago, my friend Dave Enbeck and I wrote a couple of papers about this because we were thinking quite seriously about, again, from a slightly Mara-inspired perspective, about how do you link what we've learned in psychology, in particular linguistics, as a part of cognitive science versus the neuroscience of language. And there's two issues we have, we tried to grapple with. One, which we called the granularity mismatch problem, is exactly that, which is that the grain size of problem that people in linguistics work on versus the people that neuroscience of language work on is hugely mismatched, hence granularity mismatch, right? So people in the neuroscience of language do experiments on can I find words, or can I, is there a difference between phonology, syntax, and semantics or something like that, which is relatively coarse-grained. People who work on linguistics and know something about the details of languages across languages work on extremely subtle issues across languages that are extremely fine-grained in their nature. And so the question is, and that's to us, that was more of a practical problem. That is, if neuroscientists and linguists work more productively together, and then this can be solved. That is, linguistics gives you extremely useful hypotheses, actually, and then you can hold their feet to the fire, right? You can say, and that doesn't mean that it doesn't mean it has to be reduced. There's no sense of reduction in that sense. It just has to mean, we have good evidence for this kind of stuff, and we have good evidence for that. How can we operationalize the question so we get meaningful measurements in the middle? That's a kind of practical issue. The more problematic issue is what we were talking about earlier too, which is what we call the ontological incommensurability problem. And that's a kind of philosophically deeper problem, which is just a fancy way of saying mind-body problem. Right? That is, the ontological commitments you make in psychology, computer science, cognition, or whatever, are very different to the ones that you make in neuroscience, which is stuff. Mm-hmm. Right? So the stuff of neuroscience is stuff like neurons, dendrites, receptors, oscillations, spikes. There's a parts list. The parts list of the cognitive sciences, are especially in terms of language, is very different units. Let's say morpheme, or syntactic relay. It has different primitives and different primitive operations. Yeah. The question is, are those so different in kind that there is no linking hypothesis that we can even think of? So they're ontologically incommensurable. And if that's true, then we're toast. Now, I don't believe that to be true, because I believe that the brain is the part of the body that does the language part, and not the knee or the liver. But we're stuck on that because we have equally good reason to believe that linguistics has given us very good primitives, whether from cognitive science, computer science, language, and we have reason to believe that neuroscience has given us good primitives. And so the linking hypothesis problem is non-trivial, to say the least. Yeah. And so that's an exercise for the future. But The maps and the mapping problem is just a version of that. So for me, what we work on in our day-to-day work as neurobiology of language is the map is making maps, because we're all seduced by maps. We want to have a V1 is here, a V2 is here, MT is over there, and primary auditory cortex is there, and we have often basically adopted localization as explanation. And localization is not explanation.
Is that still a problem, you think? Because it was a problem, especially.
But we still, there's plenty of talks where you see a bunch of localizations.
Feels good to see a blob light up.
And it feels a sort of intermediate level of understanding. But what needs to be said is this is just the beginning of the research, just like the correlation. This now tells me this is where I got to look and do the real experiments now. So the maps problem is simply to do, can we do better characterization? What we were talking about a little earlier about getting a really good anatomic description of the human auditory cortex.
Yeah.
That's a maps problem. That requires good technique, good research thinking about how to do it. What's the right level of characterization? Maybe it's some kind of weird laminar thing. Who knows? That's kind of doing good systematic kind of nuts and bolts anatomy. Really useful, really important. But that's making maps. It's a practical problem solvable. The mapping problem is the same as I just talked about, which is how do you map a level of representation onto another level of representation, right? So that's making mappings from, let's say, the cognitive sciences to the neurosciences. And that's, or as it was 100 years ago or more, how do you map from chemistry to physics? And as we know famously, it wasn't a case of reduction. It was a case of that physics had to change its conceptual fundamental commitments to accommodate the facts of chemistry. So it was a fact of unification or change in the other direction. So not reduction, but actually anti-reduction. And maybe to have really unified neurobiology of language, we actually need conceptual change. That is, we need to figure out whether the primitives of neuroscience and the primitives of linguistics are even right at all.
Yeah.
Some poor graduate student of mine has to deal with that, but since it's tricky business for reals, but it's an exciting problem. It's a deep problem. It's a variety of the mind-body problem. It's one of the most exciting things in intellectual history.
I want to know. I want to understand. What do you think? So I ask this sometimes at I don't go to cocktail parties anymore, but I've social gatherings or something.
Beer parties.
Yeah, beer parties. Right before my keg stand, I asked the. So let's say slavery, right? That's bad. Slavery's bad. And if we sort of take the bird's eye view and we think, okay, we've got that solved, but it's kind of embarrassing that we ever did it, right? And let's say women's rights, things like that.
Yeah.
What are we doing right now? And this can be in the world of science and figuring out brains, or just in general, whatever you're thinking. What are we doing right now that our descendants are going to look back on and think, Jesus, what? Why? How do they even think that was okay? And it can be about understanding ourselves too.
Yeah, so let me say something about. So I have a long list of things, sciencey things here, but let me actually deviate a bit from your script here. That I think that what people should be now and later will say we're doing a shitty job on is how we treat younger people and trainees, how we publish stuff. That is going to be looked on as absolutely appalling. The way we discourage, the way the system is organized to discourage people from wanting to do something that's hard and not well paid and ultimately very important, the way we have set up reward systems through grants and publications that do nothing but reward the wrong instincts. It's a system that's just absolutely shocking. And I think in 20 years or maybe 50, people are going to say, wow, you guys lost generations of wonderful, creative, exciting scholars by putting them into this ridiculous system of what counts as success and what counts as, what the meritocracy is about and how you publish and how you assign beans.
But see, you're preaching to the choir. This is like my calling. This is why I left. Part of the reason why I left, get out of the game.
Yeah, and I think that's one of our biggest problems. And that's not for our science, not just for neuroscience or cognitive science. That's, I think, really across a bunch of sciences. And I see, and I say that as someone, I care a lot about my trainees here and at the Max Planck Institute. My two job gigs, I try to do my best to support them and to help them find jobs and to not be, an annoying advisor. But, all, good intentions pave the way to hell. I mean, we do our best, and we say, look, you should just follow your hunch, and you're doing an exciting experiment, and I'm really, really cool the results you're sharing with us. At the end of the day, we say, look, really better publish that in this kind of journal if you want a job next.
Yeah.
I mean, come on, really? That's like the way we set this up. It's not about ideas and looking forwards and thinking forwards. It's about totally accommodating to some kind of weird, set up by my generation and the generation in front of me, imperialism of how to do science.
Well, there has to be some system, right? But I mean, so a lot of people hide in academia because you don't actually need to do anything often. If you don't know what else to do in your life, you can stay in school, essentially, right? So there's and hide under someone else's funding.
To some extent, that's not uniformly true, right? I mean, you have to. There's some luck required to actually get that job for the long term. It's true that there's too many people but it's not. I mean, you can't just say, "Hey, I'm here. Sign me up for this."
But the efficiency of science is you see a lot of wasted effort. Yeah,
a lot of wasted effort, and to me, the most discouraging is the extent to which we're discouraging. I mean, we're discouraging smart people. You're a good example. And people who were, committed and excited and, good at the work in the lab and good thinkers, because the system is set up to beat you down and not to make it a joyous experience. Right. So that's, I don't know what to, and I have it, in sort of a sense of self-irony. Where's my little sticker here? So a friend of mine gave me there's a famous play by David Mamet called Glengarry Glen Ross.
Uh-huh.
And there's a good movie adaptation of this with Alec Baldwin giving this monologue about how crappy all these realtors are, and he gives this amazing monologue, and it starts with the line.
You get your crumpled up paper. Yeah.
So Jack Lemmon is standing getting himself a coffee, and Alec Baldwin says, "Put the coffee down. Coffee is for closers." I have the
coffee is for closers.
That are lying around everywhere.
That's a coaster, huh? For your
that's a coaster. We have coffee is for closers, coasters everywhere. Partly, and it's sort of ironic, but not right. I mean, it's funny and ironic, but the fact of the matter is that is the thing. If you can't close and integrate yourself into a system that we've set up, the chances of success now are minuscule. And it is what it is, but are we going to stand for that? How are we going to, how am I supposed to, and I want to do right by my peeps. I love the people in my lab. They're fabulous in both my labs. These are wonderful researchers and I learn a ton and they're fun to discuss with and the ideas are cool, but I can't I can't guarantee everyone a successful future as scientists. It's just not possible. No matter how much I support them and want them to succeed, it's just, you need luck. You need familial support. You need champions who in the field who reach out to other people and say, Paul's work's the best. If you don't, it's a huge mistake not to get Paul. And you need that. You need way more family support or partner support than people are aware of.
Or you reject the system and forge your own path, like Paul is doing.
That is good, and I think that's actually absolutely reasonable. And it's not just courageous; it's also reasonable, and actually can lead to actually quite happy existence going down a different path.
We'll see. I hope so. It's hard as hell right now, but
I know. But you're doing cool stuff by basically talking about science and educating other people about it, and that will you're sort of paying it forward. That will be rewarded in some. It'll happen for you, but it presumably takes a while. But I think it's I think it's absolutely the right thing to do. So I think it's a high risk, high reward scenario for you. I think I'm optimistic because nothing is more important than kind of educating people about sciencey stuff and letting them meet scientists, because people think we're these weird people. We're just, I also go home and I have 3 kids and I whine about, laundry and school and, how shitty people are or whatever. We're all just whiners.
Yeah, sure. It's tough. It's always tough. Yeah.
To get to know people is, half the battle of doing this kind of thing that you're doing is just introducing people. Say these are just people. They're working on this, that, or the other thing, and hopefully you get a glimpse of the work, also the person, and just it's not that it's sort of a demystification exercise, which I think is extremely useful.
I do too. Yeah. So, David, thanks for spending so much time with me. I appreciate what you do and the way that you approach your science. It's slow, it's curmudgeonly.
It's curmudgeonly, yes.
But it's wonderful. And, hopefully in the future we can have you back on and talk a little bit more deeply about some of the things you're actually doing here.
That would be great. It'd be fun to do it again alone or with somebody else. It's fun to talk about work.
Yeah, we can have you and John on at the same time. So
I think that would be great fun.
Follow David on Twitter. He is at David Poeppel. And of course, you can look in the show notes for that as well. Last thing, David, I know that you have a side passion here. And you just brought up Glenn Ross. What is your dream directorial debut?
My dream directorial debut, yes. I wanted to be a director instead of a scientist. That was actually my dream career. And it's not too late. I suppose what I would really like is something like, what I'd like to direct is something like Heiner Müller's Quartet. An adaptation of the famous Liaison Dangereuse, right? The novel by Choderlos de Laclos called Liaison Dangereuse, famously remade as a movie with Michelle Pfeiffer, but adapted by the East German playwright Heiner Müller, or Heiner Müller, as we say in German, called Quartet. Funny, savage, linguistically brilliant, exciting, and with a lot of room for directorial shaping. But, now I'm a director of an institute. That's good too. It's different.
Pretty good. But for all you higher up executives involved in plays, go ahead, that are listening to this show, go ahead.
I'm up for directing, and I'm happy to do it, and it wouldn't suck.
Yeah. All right, David. Thanks for your time, and we'll talk to you soon.
Absolutely. Thanks, Paul. Good to talk to you.
Brain Inspired is a production of me and you. You can support the show through Patreon for a microscopic $2 or $4 per month. Go to braininspired.co and find the red Patreon button there. Your contribution will help sustain and improve the show and prohibit any annoying advertisements like you hear on other shows. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thanks for your support. See you next time.
Mayday, we've left our heyday, searching the coffers for empty offers. I don't